Hello everyone and welcome to our lecture on capacitors. This is the second part to the energy storage devices, inductors and capacitors. So as you can read by the definition, capacitors are parallel plates separated by an insulator, so no charge flows between the plates. And this imposes a time varying voltage drop. So that with DC or direct current, which is what we are focused on in this course, the capacitor appears to be an open in the circuit. That is why we say that no charge flows between the plates, as is written here in the slide. There are many uses for this characteristic of capacitors, of which we will dive into further in AC circuits. Now the second bullet here just gives us the equation for the root equation for looking at current with respect to time for a capacitor. So I of t is equal to C, which is for capacitance, times dVt dt. Now again, remember that we discussed a little bit about derivatives, and we're looking at the top, what's on the numerator, a difference in the function of voltage with respect to time over dt for a small differential in time. And again, the third bullet here is V of t, looking at units, is in volts. I of t for current is in amps, and C is what we call capacitance, and it's measured in farads. And the unit for that, or the symbol, is F. So given the equation for the current with respect to time for a capacitor, and given that we are introducing a constant voltage, we can calculate that I of t, which is pronounced I of t, is 0. We learned a basic concept of the derivative last lecture, in that it is looking at a difference in something with respect to something else. So the difference in something in the numerator with respect to something else being in the denominator. Think of it like a slope in a function when you have rise over run. So if a voltage is constant, there is not a difference in the numerator resulting in a 0 value in the numerator. So mathematically, we prove here that the current is also 0. So the question reads, suppose V of t is constant, then I of t must be 0. Back to concepts again, which are very, very important to engineers and engineering technologists. Let's work this particular concept, this question out together. So if the voltage drop across a capacitor is constant, we know that its current is 0. So the capacitor can be replaced by which one? A short circuit, an open circuit, or a constant? Of course, the answer is given to us here as an open circuit. That's good to know, but it's also good to know why the other ones are wrong. So why wouldn't it be a short circuit? Why wouldn't it be a straight piece of wire? If we had a straight piece of wire, we know that we would get the maximum flow of whatever charge is flowing through there. And so it couldn't be a short, because in that case we'd get maximum, whatever that value is. It also couldn't be a constant, because a constant also indicates that you have a continuous loop. And in this case, it would mean that the circuit is continuous, which it isn't. We're looking at it as an open. Okay, so let's let's break this concept down further using algebra, which I hope will help you understand calculus a little better. And again, this is not like a math class where we're deriving any calculus formulas. This is more like an applied calculus or applied mathematics for electronics. So here we're looking at discontinuation. So why is discontinuation in the voltage with respect to time not able to both create an infinite voltage drop mathematically and physically? So again, these are based on classical dynamic laws of physics. If you go to quantum physics, for example, you can have dual states in matter and energy, but we're not dealing with that here. Right? If you look at an instant change in voltage over no time difference, meaning the difference in the bottom is 0, mathematically that would create a 0 in the denominator. And we know from our mathematics that a denominator of 0 is undefined. unlike a numerator of 0. Therefore, that cannot exist. And so that we did that mathematically. But physically, we cannot have mass or energy occupying two different states at the same time. So that's why we say when we're looking at something, we look at it at time 0 and either immediately after 0 or immediately, after whatever time it's you're looking at. Because we have to differentiate that we're not looking at the same value of time for two different states of voltage. So now when looking at this slide, we see if the voltage drop across the capacitor is constant, the current is 0, so the capacitor can be replaced with an open circuit. That actually helps explain the previous slide. Looking at the equation again, I of t is equal to C times dVt dt. So suppose there is discontinuity in V of t, that is, at some value of t, the voltage jumps instantaneously. At this value of t, the derivative of the voltage is infinite. Therefore, the current is infinite. Now, mathematically, that is not, it would be possible, but in calculus, that is not one of the rules for a derivative. In order for a function to be, in order for you to be able to take the derivative of a function, it has to be continuous. So those of you who are going to move into engineering and get into higher mathematics, it's one of the confinements or one of the limits of a derivative. So this is not possible. Thus, the voltage drop across a capacitor is continuous for all time. It's another requirement. Okay. So let's work this one up together. Just a little math problem here. And we're given the conditions for voltage at t less than 0 and t greater than or equal to 0. Now, in a math problem, this will actually be given to you, so it's not going to be something you have to derive, at least for this point. So we have condition 1, and let me see if I can mark this down here. Here we go. Condition 1, my writing's not that good. V of t is equal to V naught, and this is for all times when t is less than 0. And then we have condition 2. Better. V of t is equal to this function. Now, this function is something that we either designed the circuit to be, or it's something that we've observed with a circuit that we didn't know, and we plotted a bunch of points and we get this equation. So V of t equals 15 e to the minus 250t minus 10 e to the minus 100t volts for any value of t greater than 0. So it says this expression for the capacitor voltage is valid only if the value of V naught is what? Right, so let's go ahead and plug in a value here that we know that would be valid for both equations, and that would be t is equal to 0. So at this point where we have this crossover, you say, if we plug in 0, let me put this in a different color. I'm just going to circle these terms. All right, if I plug in 0, where we have t here, what happens to this function? Like, this actually goes to 1. I'm going to cancel that out. This one also goes to 1. And we're left with the equation 15 minus 10, giving us V of t is equal to 5 volts. And so this is where we actually get this statement to prove that these two functions are valid. Again, so we're going to do just a little bit of calculus for those of you who are not planning to go into engineering or want to learn a little bit about applied mathematics here. Go ahead and skip to the next slide. But this is just to give you a little bit more background, have a little bit of appreciation where the formulas come from. So again, here we see the formula, the root equation for actually deriving everything dealing with capacitors, where we have the relationship of I of t to V of t. So I of t is equal to C times dV of t over dt. And we can do just some basic algebraic manipulation where we just simply move d of t. I meant to do this. till we get this form. And all we did here was just manipulate the equation algebraically. Now, there is something for those of you who plan to go into Cal and Cal 2 specifically, where you're dealing with integration. And this is just a simplified version of the statement, but there's a little more involved to it, where you can actually cancel out a derivative by doing an integration. Right? So, so if you had the integral of a derivative, it ends up being that same function. So it's kind of what they're doing here. They're actually doing an integration of both sides, and what we're left with is we have these two functions. The integral of I of t dt equal to the integral of c dv dt. And of course, c being a constant gets removed out of the equation, so we basically have an integration of I of, and they substitute t for tau just so that we don't have replication of t, and here we separate t for x just so that it doesn't get confusing of replacing these two variables. And so I'll go ahead and work this out for you real quick so that those of you who want, and I really hope some of you actually will take a higher mathematics course, so you can work this out for yourself. And so what we have here is, I wish I could erase just part of it. How do we do this? So I'm going to go ahead and integrate this side first. And what they've done is they've already integrated and isolated it to one side. And so what we have here is the integration of I of tau from t0 to t, giving us this equation. It doesn't. Oh, I'll turn it into this. Where we have 0. T of 0, T naught, tt, I of tau, d tau. So we haven't done anything with that, but we integrate the other side of v naught from vt of naught to t, which gives us dx, which actually gives us v of t minus, that's right, yes, minus v of t naught. All of this multiplied by the constant c. And what they do here is they actually just do a little bit of algebraic manipulation where we have yes, 1 over c. So just doing a little bit of algebraic manipulation, you guys can see that we have v of t is equal to 1 over c integration of t naught to t of I of tau. Now we actually haven't integrated this side yet, we just left it alone. d tau plus the initial voltage. Now if the initial voltage is 0, that last term right over there goes to 0. It's not a problem. But this equation will actually give us the voltage at any time, no matter where you start. Okay. So the power equation, we can actually derive the energy equation by looking at power, starting off with power. And so we have the same equation, P is equal to V times I. But again, remember this time we're dealing with functions. So P of T is equal to V of T times I of T. Now we know what I of T is equal to, and see if I can just underline those terms. We'll get that one, and we get this term right here. Right, times V of T, and then I'm putting this in a different color. Times V of T, which is right there. And so as you can see, all we did is substitute the formulas for I of T and V of T to get this larger function of V of T times I of T to actually give us what power is equal to. Now we kind of do the same thing here. When we integrate power, we actually get the energy formula. I'm not going to ask you to do this again like we just did in the previous slide. I'm not going to ask you to do any integration in this class. What I do want you to know is these final equations. So, tell me I got a square. this equation here, you will need to know. Cool. And for those of you who actually want me to work this integration out, just so you can practice, if some of you are going to take the electrical engineering course for your engineering program, if you have to take it as an elective or a requirement, learning this will actually help you in that particular class. I hope you get any in that class. They're more computational from what we do. So capacitors, just like inductors that we discussed previously, are energy storage devices. If the initial voltage drop across the capacitor is non-zero, the capacitor is storing energy. So remember in the previous equation where we had that V of T of naught, meaning we were looking at the voltage at that initial condition. If there was some actual voltage there and that was given to us, then we know that that device was initially storing some energy. That's all that means. Okay. There we go. So suppose the initial voltage drop across a 4 microfarad capacitor is 10 volts. The initial energy stored in the capacitor is what? Now, without going back to the previous slides to look at the energy equation, just get used to memorizing some of these few equations. You did really well with Ohm's law and KVL and KCL, where we had capacitance times V of T, parentheses, times I think I'm going to say squared. Oops. Let me try that again. I was trying to erase everything. Let's try this again. Okay. Okay. Yeah, it won't let me erase just my last thing. I have to erase the entire formula, or all the writings in the thing. So we know the energy is equal to, I'm going to write this a little slower so it looks nicer. W of T is equal to 1/2, and we're looking for energy input, okay? C, and we're given capacitance, times V of T squared. Dang it. It's supposed to be F. Right? So we're given the value for capacitance, we're given the value for voltage, and that's basically all we need here to find W of T. You plug those numbers in and practice doing this in your calculator, you should end up with, let me do green to make sure that you can see this in good color. Okay. Now let me show you what a problem would look like when you're given initial conditions. So here we don't actually see the entire circuit. We're just looking at a particular part of the circuit. Now this could be, these initial conditions that we're showing right over here, could be something that you experimentally found. So you could create a circuit and you find that during these time intervals, this is how this capacitor is actually behaving. Or it could just be given to you from the initial problem. But it gives us what's happening at the what's happening with current across this capacitor for time t less than or equal to 0, which is this term right there, right there. For time between 0 and 20 microseconds, which is right here. Time between 20 and 40 microseconds, and then ultimately what's happening for t greater than 40 microseconds. Now the first part of this question, which you will probably get on an exam, not probably, you will get this on an exam. And this is basically understanding how to read initial conditions. And there's no reason anybody shouldn't get this part perfectly. So if I say, find the voltage, power, and energy for time less than or equal to 0, I've sort of already given you that. Hopefully you'll see this right there. This is basically a concept question. I want to make sure that you understand the concept. And so if it says that I have zero current at time t is equal to or less than zero, we know that the voltage is equal to zero. Now the same thing for power. Initial conditions, there is no energy stored in this device initially. So that means that if I'm looking for power, which is equal to I times V, or in this case, I of t times V of t, if current is zero at t is equal to zero, and voltage is zero at t is equal to zero, we know that power is also equal to zero. P of t is equal to I of t and P of t. And again, if we have no power, we have no energy being dissipated or generated. So in this case, energy is also equal to zero. So you will have a question like this. Actually, you will have a question, and this will be one of the initial conditions I'll ask you for. I hope I will see anyone get this wrong. Now, what's going to happen next on one of your exams is I've said I'm not going to ask you to do integration. So when I give you a problem like this, especially when your first function is your current or your voltage is given to you as a function, I'm going to go ahead and give you the initial condition for V of t. So in other words, what I'm saying is I'm not going to expect you to integrate. So I will not expect you to do this part here. I will actually have it written out for you on the exam. What I will expect you to know is when I give you V of t, and I give you this whole first line, that you understand that this is the function of V of t for a specific condition. So in this case, it's the specific condition between 0 and 20 microseconds. This is how voltage is reacting. I meant to do that. That supposed to be an arrow. Alright, so there's one equation. And from that, you should be able to derive the rest. Right? So we know what P of t is equal to V of t times I of t. Well, I gave you V of t. The equation itself will give you I of t during that time interval. So remember, I of t is equal to, right up here, 5,000 t amps between 0 and 20 microamps. So right now, I'm just expecting you to do a little algebra and actually plug in V of t and I of t. I'll put this in a different color so you can see what I'm writing. Right here. And again, I'm expecting you to know how to multiply variables and deal with exponents. And again, for energy, we're going to plug it into the energy equation, which you should know the energy equation for the test. And again, you're basically going to be asked to plug in functions and multiply functions to get me this combined function right here. 15.625 times 10 to the 12 to the 4th joules. Now this describes what actually happens between that time interval, 0 and 20 microseconds. And you can even look at plugging in for a specific time unit, which is 20 microseconds. And here we plug in 20 to give us, in this case we're looking for voltage. So at 20 microseconds, this is what the voltage is. 5 volts. Again, continue with the same problem, but moving forward. Let's do this, and I'm only going to box in the last two parts because we've already worked on the first two parts that, on the previous slide. So now we're at this point right here. Looking at what's happening to this capacitor between 20 and 40 microseconds, and then looking at what happens to this function greater than 40 microseconds. Again, this integration that you see here, I'm not going to ask you to do it. I meant to do an arrow. See if I can do this. right? So you're not going to be required to do this part of the problem. And I will make sure that when I give you the problem for the exam, even when I give you one for homework, I will give you this final function for current, because you will need to know this function here. You will not have to derive it on your own. If you know how to derive it, please go through it and practice. Right, so here we're given the voltage function for this next increment of 20 to 40 microseconds. And then what we end up having is we're given this function of V of t. Remember, this is a different V of t from the initial V of t. And we're given the I of t up in our conditions, because we know what's happening right there. Okay. And so now it's just plug and chug for power, and then we kind of do the same thing here for energy. And what we're doing here is, and again, this slide's not actually showing you all the mathematics behind it, but you should be able to do this and plug in the functions and actually combine variables and exponents to give you a combined function for power and a combined function for energy. And then you can plug in the limit being 40 microseconds here at t equals 40 microseconds, and you can come up to the answer of 10 volts of what's happening at 40 microseconds. So we know the voltage and how it's behaving at 20 microseconds. We know what the voltage is doing at 40 microseconds. So let's go on to the very last part of this problem. Okay. So now we're looking at the very last case here, where we have I of t is equal to 0 at t greater than or equal to 40 microseconds. So again, I'm not going to ask you to do this part, but I will do this part for you. Or maybe not do it for you, but I will just give you the function for V of t. I actually meant to draw a box. Or I'll work this out for you. From 40, here we got 40 microseconds, all the way to some infinite amount of t. And what we're going to get is that we're going to get 10 volts. So it's going to be a constant 10 volts in this capacitor from here on out. But knowing this particular value, we can actually plug it into power, because you know the power equation, and we know the energy equation. Now remember that even though we have 10 volts, our current is actually 0. So we're going to get a 0 watts from here on out past this point. And when we're looking at energy, we know that the energy equation is going to give us, since it's related to voltage, that we're going to get 10 microjoules in this capacitor from here on out. So that tells me right here that this device, because it's not decaying, in real life it actually does decay, but it does store the energy for some finite amount of time. It's not infinite, that it is a storage, energy storage device. So during the interval between 0 and 40 microseconds, the power is positive, which is being absorbed. Energy is stored and trapped by the capacitor. So even when the energy goes to 0, the voltage stays at 10 volts and the energy is non-zero. So we've actually stored energy. And so this slide we're going to actually look at graphically what's happening to that circuit. And so we're going to go from current to voltage to power to watts and describe each one of these individually. Let me that line. Yes. Okay. So remember that initially we have two plates, and one side is negative, the other side is positive. What's happening initially in the capacitor in physics is that you actually are building up this magnetic field. It initially looks like an open to voltage, right? So we have this point where, right here, where you initially have some voltage being 0. But as this magnetic field starts building up across the capacitor, and I'm just going to see if I can do this like that, we're actually allowing some current to flow, and we're actually developing a voltage drop across this capacitor. And it peaks out here right around 20 milliamps. We didn't actually calculate for that, but Well, that's close enough. I meant to make that a straight line. But look at what's happening to voltage here before 20 microseconds and after 20 microseconds. So we can see that the slope is actually moving this. And so we can look at this as being convex. But you know that the slope here is actually very high. So we're getting up, even though it looks very light. In other words, it doesn't look like that big of a graduation, but compared to this part of the this slope of the same function for voltage, you notice that here after 20 microseconds, excuse me, that it's actually charging a little bit slower. So it's faster here, and it's a little bit slower here. And then what happens at let's see if I can do this. So if the author did this thing correctly, my line went down. But you know what I meant to do. At 10 volts, right when we get up here to about 40 microseconds, this capacitor is charged to its maximum potential, and it will actually hold that 10 volts until it's being discharged, until current is actually reversed. And again, capacitors do have some small leakage, so eventually it will kind of decay on its own a little bit. But look what's happening here. At that 40 microsecond, we're at the maximum voltage. At that at that 40 microsecond, we're actually at zero current. So at this particular point, we have zero current, and we have a high voltage, not a high voltage, but the maximum voltage potential being, in this case, 10 volts, where it stays at 10 volts, let's say to infinity, ideally, and over here at the current graph up on top, it stays at 0 amps till infinity. Now let's go and move on to the power and the wattage energy equations. So we know that P is equal to I times V. No, P equal to I times V. So this curve right here is actually a product of the current and voltage graph. So what you could literally do is actually take the values, if we knew the individual values of voltage and current, multiply them and actually plot them out and do a P versus T graph, what's happening at each point. Right? So at some time T, you're having this much power being generated from I times V. And so what's happening here is we get this maximum this maximum power, not at that 20 millisecond mark. I'm going to actually just try to guesstimate this. So I can make a straight line. Kind of straight. So you notice that here current started decreasing to 20, and down here at the bottom of the voltage, the rate of change for voltage charging in the capacitor actually changed around that 20 microsecond. And look at where 20 microseconds is on our power graph. Let's start from right here. So it's not actually reading the maximum power, is it? Same thing over here with the energy. We're not actually at the maximum energy. We're not even at the midway point for energy. But what looks like is happening here is that power, once it reaches this peak and power actually starts decreasing, we're about, and I know this graphic, I didn't draw the line perfectly straight, but we should actually be right at the midpoint of the energy accumulation. So again, I know I didn't draw this perfectly, but this actually should have been closer to the midpoint here, just like we were with the voltage. So as power is actually increasing, it's going in this direction. And we have this convex, slightly higher rate of change for energy storage. And then as power is actually decreasing, going back down to zero, again, the rate of change for energy is slowing down until it maxes out, in this case, at 10 microjoules. Now the number 10 here is just coincidence, 10 volts and 10 microjoules. and it stays there. The energy is stored there. Ideally, if this is an ideal component and we had no losses, it would be there forever. But in reality, there is some loss, and that energy stored in that device will eventually leak and go down to zero at some point. So I hope this kind of made sense for current and voltage, and then looking at power and energy for how a capacitor works. Okay, so I'm going to go over a couple of more things, which some of you already know, but again, I just want to review this. Where is my pencil? So whenever we're adding capacitors in series and parallel, so again, when we're adding capacitors in parallel, we sort of use the same phenomenon that we found with resistors and inductors that are in series. So basically, C total is equal to C1 plus C2 plus dot 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 C to the n. So in this case, I'll give you just a quick example, and I think I did this already in a different lecture. Let's just say 1, 2, and 3 microfarads. So if I had 3 capacitors in parallel, and their values are 1 microfarad, 2 microfarad, 3 microfarad, C total is just 3, 4, 5, 6 microfarads. Very simple. Now let's look at capacitors in series. So again, capacitors in series, we sort of add them the way we would resistors in parallel or inductors in parallel. So in this case, the formula for total capacitance, and again, this is for a series network, would be equal to 1 over C1 plus 1 over C2 plus dot 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 1 over C to the n. And so if we had 1, 2, and 3 capacitors in series, I'm not going to go ahead and do that math. I think you know how to do it, but for the sake of time, you would use this formula of 1 over C1, C2, C3. And that's how you combine capacitors in series, like resistors and inductors that are parallel. Now let's apply this to a very simple problem. And this is something that you will get on your exam. So find the equivalent capacitance for the circuit below, assuming V1 is 12 volts and V2 is minus 8 volts. So they're actually asking for the equivalent capacitance and voltage. So we can do this pretty easy. Let's go ahead and take a look at this series parallel network, and let's go ahead and look at these 2 capacitors right now that are in parallel. It's the easiest one to do. You got 2 capacitors, 6 microfarads and 2 microfarads. So I'm going to do this right up here, where we have CT of this parallel network, and I'll put a little P here to make sure we know that it's a parallel network. And this is basically 6 plus 2, we just put 2 plus 6, which equals, this must be 6, 8 microfarads. It's supposed to be a U. Now let's redraw this circuit. I want to make sure that everyone is can follow along. So my circuit now looks like this. And we have 8 microfarads. And we were given that this is also 8 microfarads. That's supposed to be a U. Now what happens when we got 2 capacitors in series? We'll add them the way we do inductors or resistors in parallel. I'm going to put this in a different color. So I'm going to put here C, total capacitance of this series network now. Now, having 2, I know I can use product over the sum. So I can actually do 8 times 8. And the units kind of don't matter since we're all in microfarads over 8 plus 8. And I can tell you right now, when you have the same value, and you're doing resistors in parallel or inductors in parallel, or these series capacitors that are the same value, it's a quick shortcut is if you know they're both the same value, it can't be any higher than half of that value. So in this case, since they're equal, it's actually going to be 4 microfarads. Now, for some of you who like that other formula, equals to 1 over 8 plus 1 over 8. What do we get here? Right? We get 1 over 2/8, or 1/4. 1 over 1/4, which equals to 4. And so we have 4 microfarads, in case you wanted to look at it that way. Okay, so we know that we can sort of cross out, I'll put this in red, we can cross out this answer. So this one says 9.5 microfarads at 4 volts. I know we have the right answer already checked off, but we definitely have to look at one of these 4 microfarads if we didn't know, and we were given this on the test. And now we've got to find out what the equivalent voltage is across the circuit. So let's go to another color. I'll use green. Okay, so we are given 2 voltages here. The author says that this one is dropping 12 volts, and this capacitor here is dropping minus 8 volts. And so now we can use KVL, because it actually applies here. Kirchhoff's voltage law. Right, where we have the total voltage is equal to the sum of the individual voltage drops. So here we have 12 volts, and I'm going to put addition just to say that we can keep that formula, or that definition valid, which would be plus minus 8 volts, which is really saying 12 minus 8 volts, is equal to 4 volts. And so now we're looking at 4 microfarads at 4 volts. And of course, that gives us, this is the correct answer. Now you guys should be able to do a problem like this very easily. If I give you one of these, this will actually show me that you can actually add capacitors in series and parallel, and you can apply KVL and a couple other things. But just one of these problems, I can actually assess quite a bit of your knowledge. So I'll try to make it as few problems as possible on final review. Now these last 2 slides are just some summaries of what a capacitor and an inductor looks like, what their units are, what their root equations are for describing their operation, and some other equations. Again, I'm not going to expect you to do. I'm not going to expect you to do any integration. I do expect you to understand the concept of the derivative. I'm not going to make you do a derivative. You can actually understand this with just some basic algebra, looking at the numerator and denominator of d of I of t over dt, and over here, and then looking at d of vt over dt. This is a basic algebraic concept that I think you should be able to understand. And so you will have some concept questions. And again, here, know these equations. You should be able to actually, if I give you givens in an equation, you should be able to actually calculate the equivalent inductance, equivalent capacitance. I know I said total capacitance and total inductance in the previous lectures, but I meant to say, I should have said equivalent capacitance and equivalent inductance. Both for series and parallel connected circuits. I would expect you to know how to calculate energy for both inductors and capacitors, and power. And this concludes this lecture on capacitors. At this point, you should be able to do all of this for both capacitors and inductors. The final lecture that I will put out will be on operational amplifiers. Again, that concept is going to be just as easy, I would say, as these last 2 lectures on inductors and capacitors. It's not going to be too difficult. I think that most of you who've got past the analysis part for resistors being mesh, superposition, Thevenin, Norton, I think we've kind of passed the hump already. So for DC circuits. But again, one more lecture on operational amplifiers, And that'll be it for the theoretical knowledge for circuits 1. And it'll prepare you for circuits 2, AC circuits. All right. Have a nice day reviewing this.